Thank you for the presentation and for organizing the event. So yes, I will be speaking about Astral. So today the focus is actually on AI in space cyber-physical system, which is satellites. Let's say modern satellites are requested to do several tasks that can be actually are proven to be made more efficient with the usage of AI. Some examples are in the context of autonomous operations, such as, let's say, orbital collision avoidance and dynamic mission reconfiguration. There is object detection, as the FISAT-1, let's say, project from ESA has shown that leverages AI to do, let's say, image selection and cloud filtering, and during Earth observation, and of course the more classical fall detection, isolation, and recovery that we've heard of a couple of times today. And all these, let's say, algorithms and these applications have in common, of course, AI, but a lot of other stuff like real-time edge data processing, which requires a lot of computing power. The need for tolerance, because in space we need to be reliable, and of course a lot of research, which is academic, it's industrial, and research actually relies a lot of on open platforms, which is why we are here today. And a couple of years ago, because ESA, for example, has always leveraged open source instruction set architecture, starting from the Spark, which is the, let's say, mother of the Leon class processors. But in the last couple of years, let's say, RISC-V has gained some traction, and indeed we are here in the second edition of the RISC-V in Space event. But if we also move beyond the Atlantic Ocean, we also have NASA, which has, in collaboration with Microchip, decided for RISC-V as the, let's say, next generation of instruction set architectures for the space computers. It's not only about ISAs. We also need platforms to enable research for space applications, and I can say that there is very few, not many, I would say, platforms that can allow research for space applications in the wild out there. But if you might want to go sometimes and Google the platform GitHub, you might see if some researchers in the group has developed some APIs that might suit your need. And now I have a couple of, let's say, commercial slides presenting the group, because we need to give credits to these people. The Pulp team is a team of researchers spread across University of Bologna and ETH Zurich, who mostly PhD students have been part of the team as well. And the expertise of the team is in developing open source digital APIs and systems, hardware and software APIs. Started from RISC-V cores that are now maintained by, part of them are now maintained by, let's say, industrial consortiums like Open Hardware, or in, let's say, companies like Low Risk. But we also do peripherals and interconnects and domain-specific hardware accelerators. We do a lot of Lego blocks that we build and put together to build from very low-end microcontroller systems to multi-core processors to multi-cluster systems to cover all the spectrum from IoT applications to high-performance computing. All the APIs released by the group are available open source on GitHub. And from this GitHub, there is also available Astral. Astral is a, let's say, template for a template architecture for AI applications in space. And it's actually the first open source template architectures for based on RISC-V that should be used for research, academical and possibly also industrial research for developments in space applications. It has some features, provides fault tolerance at different levels, is completely open source, so you can download it and use it the way you prefer. It is highly parametric. We will show that there are a couple of examples of integration of other APIs from in and out that can be easily integrated into the systems. Provides performance and also has a built-in development flow for VCU 118 UltraScale Plus class of PGA boards booting the operating system. Astral is built around three, let's say, two main domains. The first is a host domain, we call it like that. It's more in charge of the control part of the architecture and the platform. It's built around a multi-core, let's say, cache coherent system of based around CVA6, which is a 64-bit core booting operating system, booting Linux actually, with let's say ACE cache coherence protocol. But also has a lot of other peripherals around that can be actually enabled or disabled depending on your actual needs. We just boosted this system for reliability by wrapping the cluster of CVA6 cores around a programmable redundant unit that allows to, let's say, select independent or dual mode, dual core, let's say, lockstep execution of the cores, with also a built-in hardware extensions for real-time fault recovery. We have boosted the, let's say, extended the internal of the cores, in particular the memory management unit, and let's say more specifically the TLBs and the branch predictor for single error correction and double error detection, let's say, extensions. And we also have extended the caches of the core and the system with the ECCs as well. This is the, let's say, more control part of the system, which manages indeed the boot of the operating system, but we also want to give performance for applications in space to accelerate AI, and that's why the host domain of Astral is also coupled with, let's say, an accelerator domain, which is built on a template made of, let's say, 8 32-bit RISC-V cores that share a scratchpad memory, let's say, featuring also DMA controller and many other peripherals. We also did extensions to this cluster for space using, again, a redundancy unit for the cluster cores, allowing, let's say, reconfiguration in software to execute code in independent mode or in DMR or in TMR, depending on the criticality of the executed task, and providing also real-time recovery as well from incurring faults thanks to dedicated hardware extensions. We also have extended the floating point unit of the cores with the time repetition for let's say, error detection and correction in time. We have extended the caches with parity, and also the entire memory subsystem features, let's say, error correction capabilities with the memory banks storing the correction bits, okay, and scrubbers and so on. We also want to give, let's say, AI capabilities, not only, let's say, reliability. That's why we have a pool of hardware accelerators to accelerate 16-bit floating point matrix computations, 8-bit down to 2-bit CNN inference, and also, let's say, softmax to boost transformers execution on chip. I spoke about, let's say, flexibility for integrating other IPs. One example is the Open Titan, which is the root of trust provided by Low Risk. We have integrated it as an external IP into the system quite successfully. I will just leave you. I won't spend too much time on this because it's actually developed by Low Risk. We just use it mostly as it is, and we also have another, let's say, proof of integration from, let's say, proprietary IPs, which are the space peripherals, the telemetry and telecommand IPs, and the space wire from Thales Space Italy, which actually managed to integrate the IPs properly in the system, both in software and in hardware. I have finished with the time, so I have to go quite fast, but we have, let's say, here I have just wrapped up the results on FPGA occupation and a couple of results in performance provided by the accelerator over software equivalent benchmarks. So takeaways, I have presented, let's say, a template application for developing processors for space, which is natively full torrent. It's completely open source and is quite flexible in terms of integrating other IPs and providing flexibility from programming. So thank you, everyone.